Hi everyone, my name is Arvind Hughes and I go by Arv, and today I'm going to show you some work that I did with these people down below on how to find metal poor stars using GALAH data. Now unfortunately I can't be there to give this talk live as I'm currently hiking in the NT, but my lovely supervisors Lee and Dan should be around to answer any questions you might have at the end of this presentation. So the problem. As you all know, we have GALAH, we have APOGEE, and we have RAVE that are producing spectroscopic databases that are too large to analyze using old methods. And we're going to have to develop some tools and other methods that can analyze this data easily. But in the future, there are going to be surveys like SDSS 5, Foremost, and WEAVE that are going to produce spectra on the orders of magnitude even larger than the three before. So the tools that we develop now are going to have to be customizable and adaptable to the amount of data coming in the future. Because we want to try and find the interesting science, right? So being able to do this using efficient tools is going to be very important. So the problem today that I'm going to show is using the GALAH spectra, which has 600,000 stars, we have 4 wavelength ranges. We're going to try and identify an extremely rare type of star called an extremely metal poor star. And the process is kind of like trying to find a needle within a haystack. And we want to do this in a way that's most efficient, but also can be visualized, because I think visualizing a data set is a way of getting a good understanding of the structure of it. So how are we going to do this? Well, how are we going to do this with the spectra flying everywhere, of course. So this plot here is a TS&E plot. So the method I'm going to use today is TS&E, which we've all seen before, but TS&E in its simplicity is it's a dimensionality reduction algorithm. So it takes a higher dimensional space and reduces it into a lower dimensional space, i.e. 2 or 3 dimensions, in such a way that we can visualize it. And the beauty about TS&E is it's the structure that happens when you reduce it into a 2-dimensional plane. Well, it maintains the same structure that existed in the high dimensional space, i.e. if a star is similar in the high dimensional space, it is also similar in the low dimensional space. And what that means is similar stars, when you plot it, they lie next to each other. Now, the difference between TS&E and PCA is this nonlinearity. So PCA is linear and TS&E is nonlinear in the sense that some of this hidden structure gets lost if you assume linearity, but is retained when you can include nonlinearity. So this plot here, using the labels classified by some work that Traven did in 2017 of binary stars, cool metal poor giants, H alpha, H beta, hot stars, and molecular absorption bands, you can see that these classes are really nice and well defined. But for my method, what I've said is instead, let's inject some known metal poor stars, or whatever star you're trying to find. Let's inject some known objects and see where they lie. And so you can see here that the effectiveness of TS&E in the sense that my known stars that I've injected lie on this cool metal poor giant cluster. So in theory, if I was to overlay stars that we don't know on top of this, I can infer that the stars surrounding these metal poor stars, or in this cluster, are also metal poor. So what we actually did find, so the previous plot only included these 4, but going forward, we actually found that GALAH included this minus 4.1 and minus 7.1 star, which I've labeled as Melendez and Keller. So potentially we can find some really low metal poor stars. So putting those metal poor stars with a select line list. So this is kind of important. I didn't use the whole entire spectral range. I chose a select few lines, which I'll explain later on. But putting that in and my no metal poor stars, this is the resulting map. Now you could probably analyze this map forever, but I've highlighted up here this little metal poor cluster, which I'll zoom into further. So zooming into it further, you can see that there's like this coast that I call the metal poor coast of my no metal poor stars lying along here and the blue unlabeled stars lying on top. So now we have to try and estimate the metallicity of these unlabeled stars. And I'm going to discuss our parameter fitting method. So first of all, we had to fit effective temperature, and I had some synthetic templates to do that, where I just fit the H alpha and H beta regions of my observed to the synthetics to constrain effective temperature. And having done that, with the constrained effective temperature, I try and fit log G. Now we did this two ways. The first way, just similarly spectroscopically fitting H alpha and H beta, but also using the luminosity equation, which I've dubbed as the GALAH way, just as a comparison of the fit. And what we actually found was we actually chose the GALAH way because this was systematically underestimating log G. But we also found that irrespective of which log G method we used, we'd always get the same metallicity. So it didn't really matter too much. But for further exploration or further understanding of some candidates that we did find, this is going to be important. So then we constrained effective temperature using, metallicity using log G and effective temperature and fit the lines that we put into TSNE on the observed templates. And to fit these parameters, I used the chi-squared metric and I chose the minimum chi-squared. But in order to get an understanding of how low we can go, as it were, using GALAH spectra, we did some analysis on our synthetic templates. And using the selected line range that we used in TSNE, which was this one to this one, we actually found that we can get down to about minus 3.5 with some good certainty. Carbon didn't really affect the fits too much. But anything past, roughly 3.5 to 4, if we got a value around that range, we'd probably be skeptical about it. But that was quite interesting. So now all I'm doing here is showing you the colored of my cluster with my fitted parameters. And you can see this lovely temperature gradient going from left to right for log G. But the most interesting one is the effective, the Fe on H cluster. And you can see it going from south to north. And if you remember from my previous slide, I mentioned that GALAH can probably get down to about minus 3.5. And you see up here, this coast, and if you look at our color range, it is saying minus 3.5, but they could be lower. So follow-up work is required. So this is an example of one of my prime candidates that I found. And you'll see here that if you look at the chi-squared plot, once you get down to about minus 3, minus 3.5, the chi-squared flattens out. So it could be any one of these values really. So follow-up work is definitely required. But these purple lines here, i.e. the H alpha, H beta that I've highlighted, are the fitted regions that are used in TSNE and also in the fitting for effective temperature log G. The green lines and the blue lines represent the regions that I also used in the TSNE fitting and the fitting of my metallicity in the parameter fitting. But what we also found after doing lots of iterations on this, we found a lot of potential metapore stars actually had showings of this oxygen triplet line. So we included this later on in the TSNE method, but to try and remove any looking metapore stars that had the oxygen triplet in it, which is quite interesting too. So here's just a breakdown and zoom in version of the plot before, looking at our lines. And the top panel represents a random star, the bottom panel represents the Melendez star, and the middle one represents our candidate. So you can see the top one has a few features, whereas the two lower panels, they look quite similar. So this is potentially even lower than minus 3.5. And now we have our bird plot, which shows that most of our candidates, like our literature stars, are cool giants. But it was also interesting that we found roughly 20 or so stars that sit down here, which are potentially main sequence turn-off metapore stars, which is also quite interesting. So to conclude, today what I've shown is using TSNE and some known stellar types, you can potentially find even more candidates for that given stellar type within your spectroscopic database using TSNE. And just remember, TSNE is a nice visual way of doing this. It's not just like plugging into a black box and seeing what numbers spit out. You can actually visualize the potential similarities, so it's quite useful. And we've also shown that you don't actually have to use the entire spectrum to do the fit. You can also just use some select lines to do the fit, and it'll also give you the similar TSNE map, as well as spectral parameter fitting. And we've also shown that using GALAH wavelength ranges, we can actually get down to minus 3.5. And lastly, we found roughly 90 candidates, with 70 being less than -3, 20 being less than -3.5, and roughly 20% being these potential main sequence turn-offs metal poor stars. And that's what I have for you. Thank you.
Okay, so I love that he began by making sure to point at his supervisors. So if anyone has questions, Lee and Dan are both here, and you can ask them questions. So Simon Campbell, what do you want to ask?
Hi, thanks, Arv. Nice talk. Are you finding carbon rich metal poor stars, or just like normal metal poor stars? Because
I'm not sure what none of the candidate spectra I looked at seem to have like really strong molecular absorption features. I mean, how much do the GALAH spectra have in terms of carbon, Sarah?
Not a ton, but I mean, Thomas is really the expert on this.
There's basically nothing. Unless it's super high in carbon, you won't see it. And the reason is that the only diagnostic we have is a carbon-2 band, so C2. So unless your carbon abundance is, +2 or +3 in these stars, you won't see it.
but so below, I mean, so it's sort of cut off at -3.5, I think it was. Below that, most stars are carbon rich, right? They have huge amounts of carbon, and so that's pretty much all you see. I think is David Yong here. You would know. So maybe
it has to be really high
push lower. To push lower, maybe need to look at carbon. That's just an idea.
You mean to constrain the metallicity better, but well, I guess that's not really going to constrain the metallicity because there's not like a one-to-one relationship between carbon and metallicity. Yeah.
No, but maybe
like
two points. So if you can't see any iron, then look at carbon. If carbon's huge, then
Yeah, I guess what it makes me think of is that in Anka's presentation about the pristine work, and probably Gary, who has his hand up, will say the same thing. That can make it hard to determine very low metallicities because it shows up as absorption. But this is a completely different method, and so I don't think, because there's so few carbon features in the spectrum, I don't think that that's a problem here.
It's a blessing and a curse that there is no carbon sensitivity in GALAH spectral ranges for these stars.
Okay. Thank you.
And now, Gary, let me let you speak for yourself. What did you want to say?
No, it's really a question. Have you cross-matched your candidates with the SkyMapper photometry to confirm whether they're metal poor candidates? And given that they're brighter than 14, chances are we have a 2.3 meter spectra of them already. And maybe they're in our list of extremely metal poor stars that we've been trying to follow up. On the other hand, we don't have that many that are brighter than 14. So it would be interesting to do a cross-match.
I don't think we've done an explicit cross-match with SkyMapper photometry, but I think we would be very happy to talk to you about that and also potentially follow up with the 2.3 meter.
Yeah, well, that's fine. Happy with it. Send us the list.
All right.
It looks like Jake, other questions? I was just going to say, it looks like Jake Clark was asking about the degeneracy between log G and effective temperature using spectra. Could you use stellar magnitudes? Yeah, so we actually did end up using the luminosity, the same formula as for GALAH for doing the log Gs. Basically, yeah. So I think we followed your suggestion.